In this video, we are going to discuss the idea of optimization in mathematics, and then we will work through an example of optimization. Optimization is basically the process of finding a maximum or a minimum in a real-world situation. So some examples of quantities that we might want to maximize or minimize would be maximizing profit, for example, if we were owning a company, or minimizing cost. Or we might have a situation where we have a fixed volume, but we might want to minimize surface area. That would be in a case, for example, if you were constructing, let's say, a cereal box, a box that would hold cereal, and you have a fixed amount of cereal that's going to be in the box, but you want to minimize the amount of cardboard used to make the box. So that would be finding a minimum surface area. So there are all different types of quantities that we might want to maximize or minimize in the real world. We'll work through one example right here. We'll consider a rectangle with the largest area that can be inscribed within a semicircle of radius 4 inches. And we want to write a function of a single variable that models the area of all such rectangles. And then we'll determine the domain. So it can seem a little overwhelming at first, and I would certainly recommend by reading the problem several times and attempting to draw a diagram. So we're looking at a rectangle, and we want it to be inscribed in a semicircle that has a radius of 4 inches. So I'm going to begin by drawing a diagram of the semicircle, and I'm going to go ahead and put it on the coordinate plane. So I'm going to put it on the XY axis and go ahead and count out from the origin to the right 4, up 4, and left 4, and then just do my best to draw a semicircle. It doesn't have to be perfect, it's just a sketch. So here is my semicircle. And I should note, you don't have to put your semicircle on the coordinate plane, and I'll show you in a little bit how to do this without putting it on the XY axis, because that's another way of drawing your diagram, of course. So now, to inscribe a rectangle in a semicircle, that means that the vertices, the corners of the rectangle, are going to touch the semicircle. So in this case, we're looking at having one corner be in the first quadrant, one corner in the second quadrant, and then the base of the rectangle will be along the x-axis. So I'm just going to pick a point somewhere on the semicircle, and that's an unknown point. So I'm just going to label it as xy, and then I'm going to come straight down and across and draw in my rectangle. Here you see the second vertex or corner of that rectangle that will lie on the semicircle, and then we'll have the last two vertices of the rectangle that lie on the x-axis. So this would be one possible rectangle. And remember, as we move the coordinate around, as we move this coordinate xy around the semicircle, then the rectangle is going to change shape. It still will be a rectangle, but it'll be a different size rectangle. So now we want to go ahead and try to write a function of a single variable to model the area of this rectangle. So our goal is area. So we're going to begin with writing an area function. And since we're finding the area of a rectangle, we know that we can find that area by multiplying the base of the rectangle times the height of the rectangle. And if you learn that as length times width, that would be the same thing. You can do either one. So I'm just going to use A for area. And this means I need to look at my diagram, and I need to do a better job labeling this diagram because I need to find out what the length of the rectangle is. So looking at how I currently have this labeled, starting from the origin, we would go to the right a length or a distance of x, and then we'd go up a distance of y to get to that coordinate x comma y that's on the semicircle. And if I were to go to the left from the origin, I would also go left a distance of x, and then once again up a distance of y. So what that means is the base of my rectangle, which goes all the way here from the left side to the right side of the rectangle, it's really x plus x, which means the base of my rectangle is 2x. And then the height of my rectangle is y. So my area formula will be 2x times y when we do base times height. Now as I look at this equation here, area equals 2xy, this equation is in terms of two variables because we have x as well as y. That is not going to be a function of a single variable as the directions instructed. So this is telling me that I'm going to need to eliminate one of my variables. So I can't move any further right now with area equals 2xy. I need to go back to my diagram and figure out another way to relate x and y. How can I relate those unknowns in this scenario? And there's a few ways of looking at this. One way to look at this would be to consider the equation for the circle. Since we know that it is a semicircle with a radius of 4, and we have already studied the equation for circles, then we could go ahead and use the equation for the circle as our second equation. And just so you know, I normally call my second equation that I'm going to use to try to eliminate one of my variables, I often call it a constraint equation. You don't have to have it labeled, but that's just what I tend to call it. It's my constraint equation. I like that word constraint because you can see that this point, xy, we have a limitation on this point. We're limited to being on the semicircle. We can't be somewhere else. We have to be on that semicircle. Therefore, the equation for a circle, it's centered at 0, 0, will be x squared plus y squared equals the radius squared. And in this case, the radius is 4, so this becomes x squared plus y squared equals 4 squared. In other words, that's equal to 16. So we have this second equation, I'm calling it my constraint equation, that relates the variables x and y. So we can take this equation and solve for either variable, it doesn't matter which, and then we can use that equation to substitute into our area model and eliminate a variable. So I'm going to go ahead and solve for y by subtracting the x squared. And then I will square root both sides. And typically, that requires us to have a plus or minus. So plus or minus the square root of 16 minus x squared. Now, if I were to plot this on my graphing calculator, the positive would get me the top half of the circle. The negative would get me the bottom half of the circle. In this case, I really only need the top half of the circle because this is a semicircle. So I'm just going to go ahead and use the positive value, which would be the square root of 16 minus x squared, and then I'm going to substitute that equation into my area model. So therefore my area model becomes 2x times the square root of 16 minus x squared. And now you see I have only one input variable. My input variable is x, so I have achieved the goal of writing a function of a single variable. The only other slight adjustment that I'll make is the directions here specifically said it wanted a function. So I am going to go ahead and replace this a and actually use function notation there. So I'm going to write this as a of x is equal to 2x times the square root of 16 minus x squared. And this will be my function of a single variable modeling the area of all possible rectangles inscribed in this semicircle.
Now let me go back and discuss this constraint equation in a slightly different way. Because if you're a person that didn't immediately think about the equation for a circle, x squared plus y squared equals r squared, that's okay. You could also come back to your diagram and you could think of a little right triangle here. From the origin, if we travel to that point xy, we end up creating a right triangle. The base of this right triangle is x. The height of that right triangle is y. And then the hypotenuse of this right triangle is actually the radius of the circle. And we know that the radius is 4. So another way of generating the constraint equation is to think about just computing Pythagorean theorem, which would be x squared plus y squared equals 4 squared. Using Pythagorean theorem, a squared plus b squared equals c squared. But you'll notice that's the exact same result that we got when we were thinking about it as the equation for a circle. And that's because the equation for a circle comes from the Pythagorean theorem. So that's kind of an alternative way of thinking about it. So now that we've written our function, let's move on to try to compute the domain. And we want to consider the domain in this context. So what are the largest and smallest values that x could take on, basically? So if we look at our diagram, again, starting at the origin, the largest that x could possibly be, since x is this horizontal distance, would be 4. Because if x was any larger than 4, then we would lie outside of the semicircle. And we need to be within that semicircle. So the largest that x could be would be 4. But in reality, if x was equal to 4, then the y value there would be 0. And we wouldn't have a height of a rectangle, so we wouldn't actually have a rectangle. So we can say x could be any value between 0 and 4, but we were not going to include 4. But if we go to the left, we see that x could also come over here to the left, and it could be possibly -4. But we do have that same issue that if x was -4, then we actually wouldn't have a rectangle because the y value there is 0. So it looks like our domain is going to be all of the x values between -4 and 4, but I'm not going to include either -4 or 4 because then we wouldn't actually have a rectangle to compute the area of. So now that we have our function written, we can move on to part B. So part B is asking what value of x will give the largest rectangle possible. So the largest rectangle implies we're trying to find a maximum, the maximum area. So this is the point where in an algebra class, I'm going to allow you to grab your graphing calculator and graph the function, the area function here, what we're calling our area model that we created, and then use your graphing calculator to calculate the max. Now, in a calculus class, we would learn some additional calculus ideas that would actually allow us to calculate the maximum by hand. But in an algebra class, we'll do it on our graphing calculator. So please pause the video, grab your graphing calculator. A little reminder that you'll be using the Y1 section of your graphing calculator in the upper left-hand corner where you have your y equals button. You will be basically putting your area model into your Y1, and you'll type it exactly like we have it written, 2x times the square root of 16 minus x squared. And then always choose zoom, find that zoom key, and I always want you to start with zoom 6. Remember, zoom 6 is zoom standard, because that will change your viewing window back to a standard viewing window. And then adjust your window and go ahead and calculate that maximum and then come back. So hopefully you calculated your maximum. On a standard viewing window, I hope you noticed that you actually couldn't see the maximum. You had to change your Y max a little bit. I changed my Y maximum to 20, and that was plenty. That allowed me to actually see the maximum that was in the first quadrant. So once you calculate that maximum, I recommend that you actually write down the entire coordinate that you get off of your graphing calculator. So in this case, it was approximately 2.83, if I round to the hundredth, comma 16. And that was the maximum that the calculator generated. But I do want to remind you, on the calculator, it always labels these values as x and y. But we have to look back to our model. And our model here, we have a of x, which means my input variable was x. So I'll label the 2.83 as x. But my output variable was area. So it's more accurate to label this coordinate as x comma a, so that we remember we have an x value and then we have an area. And that's also going to help us to answer the question. For part B, it asks for what value of x will give the largest rectangle possible. So our answer for part B is an x value of approximately 2.83. Now for part C, it asks for the area of the largest rectangle possible, and the area is our y value. So our maximum area is 16. And then if you go back to the original problem, it said the radius was 4 inches. So this would be 16 square inches since it is an x value. And that will be the largest area that we can inscribe in a semicircle with a radius of 4.